Hello, Honors Algebra 2 students. This is Mrs. Fellon. We are actually on graphing rational functions in this section. So I did my own kind of side notes here. We are going to do lesson like 7.2 notes, but that is, we're going to do that in the next or one of the next videos. So if you haven't already, either if you're in class, I might have given you a hard copy of this, but it's also posted on Canvas for those of you who are virtual. I would encourage you to print this on like one-sided, so don't do back-to-back, only because there are some graphs that we're going to be using when you do this investigation, when we do most of this in class, and you're going to need to cut some stuff out instead or tape it, and if it's back-to-back, that will obviously pose a problem. So before we do the kind of the in-class activities, I want to kind of go over some preliminary stuff. So in this unit, we're talking about rational functions, and basically what a rational function is, and if you notice, here's some examples up here. A rational function is a ratio, which in other words is a fancy way of saying fraction, of one polynomial to another polynomial. So if you notice here, I have a quadratic on the numerator and I have a linear on the denominator. In the second rational that we're going to use for my example, I have a linear on the numerator and a quadratic on the denominator. And so a lot of this kind of relates back to what we've already learned about with like exponent properties and so forth. Like if you have a quadratic and you divide it by a linear, so if you have a ratio, right? So think about if I had just x squared over x, you would tell me that this reduces. So x squared over x reduces to x because you can kind of subtract those exponents. So in theory, a quadratic divided by a linear results in a linear, right? So this answer is a linear. If you had a cubic divided by a linear, so something to the third power, so let's change this to a 3, then how this would change is now our result is a quadratic. So that's one of the things that I want us to kind of keep in the back of our minds, just kind of understanding like the ratio between the numerators and the denominators. And then we're going to kind of tie in some of the other stuff that we've learned throughout the course of this year to kind of help understand what these graphs look like. So these graphs are graphs of rational functions. Unlike other functions, don't have necessarily a specific looking graph. Like a parabola looks like a U, right? A linear function looks like a line. A cubic has that kind of that turn in it, a log function, a exponential function, all the different ones, sine, cosine, tangent, all the ones that you've talked about have kind of a distinctive pattern, whereas a rational function has many options. And so I'm going to walk you through how you can go ahead and graph them. So there are some preliminary work that we need to do in order for you to kind of get a good feel for how to graph a function. And so the first thing we look at is how to find an x-intercept. And so if you're looking at, thinking about this algebraically, when you find an x-intercept, one of the most basic ways, so like summary, how do you find an x-intercept for all rational functions? So this is kind of going back to our concept of just how to find an x-intercept in general. An x-intercept is when y is 0. So if I have this function and I'm writing it in function notation, but I can change it into non-function notation. If I wanted to find a x-intercept, I would set 0 or set y equal to 0. That would be my process, okay? So this is in general what you're doing. So I'm just going to jump down here to this last thing. So I said find the x-intercept, and I'm going to use my two examples here. So I'm going to go ahead and rewrite this. So x squared over x minus 1. And then the second equation, I'm going to set y equals to 0, or if you noticed, p of x equals to 0. And I'm going to do x plus 3 over 2x squared minus 8x. All right, so if we're solving these, again, you want to, in theory, what you want to do is kind of multiply both sides by x minus 1 here, or you could cross multiply. Either way, you're going to end up with x minus 1 times 0, which is going to give me 0. Same thing over here. If I multiply both sides of my equation by 2x squared minus 8x, or if I cross multiply, I'm going to still end up with 0 equals x plus 3. So then if I square root both sides, I get 0 equals x. And if you remember, because that wasn't x squared, that would be a double 0. So think back to our polynomials unit when we talked about a double 0 and what happened on the x-axis when there was a double 0. If you remember, it bounces off the x-axis. So part of that's going to hold true for all of these functions too, because we are, in theory, graphing polynomials. We're graphing quadratic, we're graphing a linear. So it's going to have those same characteristics that we talked about in, what was it, unit 3 or 4, whatever it was, back first semester. In this one, if I go ahead and solve for x here, I'm just going to get x to equal -3. So again, what we're going to do is we're going to write that as a point because we are talking about an x-intercept. So there was no doubles or triples or nothing fancy. It was just a single. So if you hadn't already noticed, so if I gave you any function, right, any rational function, I set it equal to 0 to find my x-intercept, the denominator really doesn't matter. And the reason why is because you're always going to multiply that denominator by 0, and it's going to cancel out. It's going to give you 0. So kind of the shortcut way, and this is what I'm going to write up here, how do we find an x-intercept? If you have a rational function, the shortcut way, or the process I would like you to think about, is all you're really going to do is you're going to set the numerator equal to 0, and then solve for x. So because of the fact that when you multiply by 0, or multiply both sides by x minus 1, either way, you're going to get 0 times something, whatever that is, and it's always going to equal 0. So the denominator is never going to matter in this scenario. And so what we're going to get is always going to basically just, if we just take our numerator and set it equal to 0, that's going to give us our x-intercepts. All right, so there are some other things in rational functions. There's all kinds of asymptotes. So it says, when do we get an undefined answer? These will be some of the asymptotes. So think about when we get an undefined answer. Think about how did we know when tangent was undefined? So I'm just going to take a little side note back to trig, right? If I did tangent of pi over 2, okay, so this was at the point 0, 1. Tangent of pi over 2 is y divided by x. So my y value divided by x value. I get 1 over 0, which then that tells me it's undefined. Remember what the graph of a tangent function looked like. Any place where tangent was undefined, there was that asymptote, that vertical asymptote. Same thing holds true for rational functions. So in order for us to determine, like in a rational function, so if I take my two rational functions, how I'm going to get an undefined answer is I'm going to have 1 over 0. That's always going to result in something that's undefined, okay? Because 1 divided by 0 is undefined, right? We can't divide something into 0 pieces. And so that's how you're going to get an undefined answer. Whereas obviously in tangent, we looked at the graphs and so forth, but in rational functions, because you have a fraction, we know that this is going to be, we're going to have an undefined answer anytime this denominator is 0. Anytime, whatever, I don't care what the denominator is, anytime that denominator equals 0, you're going to have a relationship of something over 0. I don't care if it's 1 or 552 or x squared. It doesn't really matter. Anything divided by 0 will always result in undefined. So to kind of recap here, what we're looking at is, in order for us to find undefined answers, which is going to be some of our asymptotes, we need to look at when is the denominator going to be 0. Because anytime that denominator is 0, you're going to get this some number or some value over 0, which is going to result in undefined. So kind of our shortcut way to find x-intercepts, we set the numerator equal to 0. To get our vertical asymptotes, so our asymptotes, we're going to set the denominator equal to 0. So that's one of the things I definitely need you to know, kind of these main important things, x-intercepts and asymptotes. All right, how do you get the asymptotes for all functions? Again, what we're going to do is, I probably should have wrote there, we're going to set the denominator equal to 0. If we get an undefined answer, how does that look on a graph? And so what I was getting at here is this idea of like tangent, right? When we did it algebraically, and I just said find tangent of pi over 2, your answer was undefined. But then when we changed it to a graph, how did that show up on the graph? Well, those were those parts. If something is undefined graphically, it means the graph does not exist there. Okay, so there's like a gap in the graph. And so what we're looking at is undefined. We're looking at algebraically, it means when 1 is divided by 0. This is how you get an undefined answer. Graphically, an undefined answer is going to result in an asymptote. I'm going to be very specific here. I'm going to say a vertical asymptote. We haven't really talked about functions yet that have both vertical and horizontal and something called other asymptotes. In this unit, we're going to get into all different kinds of asymptotes. So we're going to kind of do a variety. So when we have something that's undefined like this, that denominator equal to 0, that's what we're going to get is those vertical asymptotes, the ones that are up and down. All right, so for our examples over here, when we did the t of x and the p of x, so if I had my function and I asked you, we already knew how to find the x-intercepts, right? We set the numerator equal to 0. If I said find the asymptote, you would take this denominator, set it equal to 0, and write it as x equals 1. And so remember, the reason why our asymptotes are gonna be vertical is because this x equals 1 is a vertical line, right? It's not y equals 1, which would be horizontal. X equals 1 is a vertical line. Leave it as an equation. This is an equation of a line. Don't write it as 1. Don't write it as 1 comma 0 like a point. Write it as an equation. Same thing goes with the p of x equation. We had x squared over 2x squared minus 8x. So again, numerator doesn't really matter because all we're looking for is when is that denominator set equal to 0. Probably, this is going to go back to our lovely quadratics. Remember our glory days of factoring. If you are struggling with factoring, this unit's going to be challenging for you. Lots and lots and lots and lots of factoring. So if you need a little practice on it, great, because this unit is going to give you tons of practice. And so we're going to dive more into factoring when we get into like multiplying rational functions and dividing and all kinds of fun things. But for now, when we solve a quadratic, remember our first step was to factor out a GCF. So think back to those rules we talked about when you're solving a quadratic. So if it's two terms, a binomial, you always look for a GCF first. And so in this case, I factored out 2x. I set each of my factors equal to 0. So I take each of those. So that means this particular function, this p of x function that I had here, is going to have 2 vertical asymptotes. So yes, a function can have more than one vertical asymptote. All right, let's switch this over to the next page. So we're just gonna I'm just gonna walk through an example tomorrow, or when we're in class, when we're doing this. So it's really important that you obviously watch this video before get into class. So when we do this in class, you're gonna be doing this on your own. So I wanted to go through an example just to make sure that you're good with this. And that way, when you're in class, if you have questions, obviously I can answer, but hopefully a lot of this is making sense. All right, so it says, plot the x-intercepts on the graph, then put a dotted line for the asymptotes. We always want at least 3 points on each side of the asymptote to see the shape of the graph. Okay, so these functions are gonna be really weird. So I'm just gonna forewarn you. We're just gonna take this example of the t of x equation. So remember, we talked about our x-intercepts, set the numerator equal to 0. And this was the one where we got that double 0 of 0, 0. Again, write it as a point because it's an x-intercept. The vertical asymptote, we set the denominator equal to 0. We get x equals 1. Leave it as an equation. So on my line, I am going to go ahead at x equals 1. I'm going to put a dashed line. I'm also going to put an x-intercept at 0, 0. So what this allows me to do is give me some parameters for my graph. So that's always where I start. I start with the x-intercepts and I start with the vertical asymptotes. So it's going to give me some idea of where this graph is going to be located. Now, because there's an asymptote, if you think back to your tangent graph, because that was the one we had probably the most vertical asymptotes on, right? So think back to your tangent graph. There was breaks in the graph. So it was like that, line that did this over and over and over again. Right? So it's like that curve, right? And so it would be a continuous graph with the exception of the fact that we broke it because of those asymptotes. Why that's important is because an asymptote breaks your graph, which means there's something to the right of your graph. There's a piece of your graph to the right and there's a piece of your graph to the left. So a vertical asymptote is like if you were to draw, a complete parabola or whatever it is, a complete graph, and then you put like a break in it. And so again, there's, when you look at this function, you have to think about there's something to the right and something to the left. So this is where your table is going to come into play. And, a lot of this is going to be, we're obviously going to go through this in a little bit more detail now, but, as you get more comfortable with this, it becomes a lot easier. So when you look at this function, this is 1, right? So you want to find some x values that are greater than 1. So I want 3 values that are greater than 1. So how about 2, 3, and 4? And I put them at the end here just because I want it to be in order. Then so always what I look at is I look at values that are greater than the asymptote. So x values that are greater than my asymptote, x values that are less than my asymptote. Well, my values that are less than my asymptote, I already know 0, 0. So let's pick like negative 1, negative 2, and negative 3. Because we already know 0, 0 is already on here. Okay, so I wanted 3 additional points on either side of my asymptote. All right, now the fun part comes into play. You can use your calculator if you so wish, or you can just, do the math, right? So you're plugging in -3 into your equation and solving for x. So if you didn't have a calculator, you plug in -3, you would get 9 over -4. 9 over -4. So that'd be -9/4. So about, I don't know, 2.25. So again, we're going to estimate where these are going to graph, so you can write it as a decimal if that makes you happier. Plug in -2, I get 4 over -3. So -4/3. Plug in -1, I get 1 over -2. So -1/2. Plug in 2, I get 4 over 1, it's 4. Plug in 3, I get 9 over 2, which is 4.5. I'll just write it as a decimal. Plug in 4, I get 16 over 3. So again, that's about 5.3 repeating, 5 1/3. Okay, so what that does is just give us some points. So let's graph those on our grid. So I'm going to graph the 3 to the right. So this is 1, 2, 1, 2, 3, 4, 5, 6, 7. We'll go up to 7. All right, so at the point 2, 4, 1, 2, 3, 4. We're about right here. How about 3, 4 1/2? Okay. And then 4, 5 1/3. 1, 2, 3, 4, 5. All right, so what's going to happen here is this graph looks like a line here. However, we know this graph, so it's going to come like this. Each of these branches, we call these branches like the two pieces of your graph. We know that this branch here has to connect, like it has to approach my asymptote. So what I don't know now is, does it go down like this or does it go up like that? So what I want to do is maybe get a feel for, like, if I plugged in 1 1/2, what would I get? So grab your calculator because it's easier to do that in your calculator. If I plugged in 1 1/2, 1.5 squared is 2.25, divided by 1 1/2 minus 1 is just 1/2. So I get, at 1 1/2, I get 4 1/2. 1, 2, 3, 4. So it's up here. So what this tells me is my graph is going to do this. So there's an asymptote there for a reason, which means that the graph was, imagine you were drawing a complete straight, or a complete continuous graph, and then you just kind of chopped it off, right? You made like a little cut in it. So we knew these points were here because of those ones. And so your line has to approach your asymptote either this way or this way. And so that's why I kind of went with that extra point, just to kind of get that feel. We know that 0 is 0, so -1, let's go with 1, 2, 3, -1 and -1/2. So about right here. -2 and 4, -4/3 is like 1 1/3. -3 and about 2 2/5, 2.25. So that's about like right here. So same deal. This one's like this. Do we want it to go up or want it to go down? And so you will learn at the more graph that this one has to go down, because if this side went up, this side has to go down because this was like cut in half. But to kind of get a good feel, pick a point. So like again, if you don't know if it goes up towards the asymptote or down towards the asymptote, pick a point that's in between, so like 1/2, and plug it in. So 0.5 squared should give me 1/4, or 0.25, divided by 0.5 minus 1 be -0.5. Whoops. And I use the negative sign. And I get -1/2. So this is why at positive 1/2 of an x value, I get a y value of -1/2, and so I know that it curves down. So this is going to be my graph for this, okay? So what we're going to be doing in class is we are going to be graphing a whole bunch of functions, but we're going to start by looking at our x-intercepts and our vertical asymptotes, and then I'm going to give you the graphs. So we're going to kind of do this part in class. So I'm going to ask you to find x-intercepts for each function, your vertical asymptotes for each function. Let me go over how to find the domain in set notation, and then I want you to match the graphs. So like, for example, these are all your graphs on this page here. So I got them for you. You don't actually have to physically graph them. But without a calculator, with using a calculator as minimal as possible. We're going to go through there's like 6 or 8 examples on this little packet here. And you're going to match up which graph with which function. Let me go over how to do a domain. Okay. So the domain is actually down here at the bottom. So we're going to do set notation for domain. I prefer set notation with rational functions. And so I'm probably going to ask you when you do domains to always write it in set notation. All right, to start, you're going to kind of do the same thing as we always do. Start with all real numbers. And so the notation is all values of x such that x is an element of the real number system. Okay, so let's think about our graph, okay? We know that the domain means all x values. There's only one x value that doesn't exist here. So, and that's right here. That's when this vertical asymptote is at 1. So a nice way of kind of remembering how to do the domain, it's always going to be, always, always, and always, all real numbers except for your vertical asymptote. So in my example here, it's going to be all real numbers except when x does not equal 1 or when x cannot equal 1. So in like how I want you to think of it, again, is when you are thinking about doing domain, I want you to think of all real numbers except your vertical asymptote. And I just use that abbreviation for vertical asymptote. So that's how you're going to write it. We'll worry about range later in the second part of this. And so I'll kind of come back to that here in a bit when we go over the next little section. But that's how you do domain. All right, so you have enough information to be able to do our activity that we're going to be doing in class. And so if you have questions prior to the activity, please make sure you ask. And that should be it for now. All right, thanks everyone.